Hello friends, welcome to EC Academy. In this lecture, let us understand retrograde P-Well process. In this video, we will understand what retrograde P-Well process is, why we use it instead of older method, and a step-by-step diagram of how it is made. Before we understand the step-by-step method, let us understand why we need this process. In older days, we used something called as conventional P-Well diffusion. You just imagine dropping an ink on a wet paper. What will happen? The ink will go down the paper, but it also spreads sideways, right? Similar to this, when we do thermal diffusion on a substrate to create a P-well, it will also create the lateral spreading, as you can see from this diagram. This sideways spreading is known as lateral diffusion or lateral spread. So one of the major disadvantage of this lateral spread is that if the material spread sideways too much, we cannot put transistor close to each other. So to overcome this limitation of older method, we use an advanced technique which is called as retrograde P-Well process, which uses high energy implantation as shown in this second diagram. Now let us understand the new method. It uses high energy implantation, which means instead of heating and letting the material spread, which is used in thermal diffusion, we use high energy boron implantation, which means it is similar to shooting a tiny boron particle straight down into the silicon, just like little bullets, by using very high energy. So due to this, there will be reduced spreading. Because we shoot the boron straight down, the implant dopant remains at a controlled depth. This will reduce the sideways spreading as shown in this diagram, or we can say it will reduce the lateral diffusion. So due to this, we will be having a better packing density. So as you can see carefully, because the spreading is less compared to older method, we can put transistor closer to each other. This will enable smaller transistor spacing and it will also improve the packaging density. So which means we can have more transistor in less space. If we have more transistor in this less space, we will be having a faster and better transistors. So using this new method, we can control three important things. First one is junction depth, then the sheet resistance and the threshold voltage. So all these three can be controlled independently, which is a very high advantage of the new method. Now let us compare the conventional method against the retrograde implantation. If we take the conventional method, which is the thermal diffusion, it will have uncontrolled lateral diffusion, as you can see in this diagram, and it has the larger transistor spacing, which means the silicon space will be wasted and the parameter controlled is coupled or dependent on each other. So which means we cannot independently control different parameters. In the retrograde process, which uses high energy boron implant, we can have the controlled depth and less lateral spreading. The transistor spacing is small, which is enabled by contained spread. So spreading is less, that's why we can have large number of transistors. And the parameter control is independent, which means we can independently control the depth, resistance and voltage of the transistor. Now let us understand the step-by-step explanation of retrograde P-Well process. In the first step, we'll start with N-type substrate. On the top of this, we are having the oxide or nitrate sandwich layer and a thick field oxide layer, which is about 8000 Armstrong thick. In the next step, we put a layer of photoresist, which is about 200 micrometer thick. You just imagine this photoresist like a stencil, which covers the part of the chip which we need to protect. In the same step, we will perform a very important action, which is boron implant. We perform boron implant using very high energy between 300 kilovolt to 600 kilovolt. The boron shoots straight into the open area to form the P-well, which is about 1 micrometer deep. If you see this diagram carefully, this high energy implant will penetrate right through the thick field oxide to form something called as channel stops. This is very important for stopping unwanted electrical currents. After the formation of P-well, in the next step, we will grow polysilicon and gate oxide as shown in this diagram. And in the next step, we add the highly doped regions called as P plus and N plus. And in final step, we put aluminum contacts so we can connect our transistor wires. Let us summarize the process. In the first step, we use retrograde P-well process to avoid the problem of old thermal diffusion. Then we use high energy boron implant between 300 kilovolt to 600 kilovolt. So this high energy boron implant will stop sideways spreading, which means it will stop lateral diffusion, and also it allows independent control of different parameters. So three important parameters that we can control is junction depth, sheet resistance, and the threshold voltage of the transistor. This is about retrograde P-well process. I hope you have understood the topic. Thank you.